Hello everyone, my name is Wang Ke. Today I will be presenting our paper, CLAD, a contrastive learning-based approach for background debiasing. First, some backgrounds of our paper. Convolutional neural networks trained with a fully supervised setting have been shown to be highly biased towards background features, and the variations in the background would cause significant drop in classification accuracy. This is commonly known as the background bias and was extensively shown through the background challenge dataset created back in 2020. Our goal in this case is to introduce a way for background debiasing in image classification task. Through our method, CLAD, we learn feature representation space which is robust to background variations. We do this through a contrastive learning-based approach, where we encourage the feature similarity between samples with similar foregrounds, and also we penalize the feature similarity between samples with similar backgrounds. In contrastive learning, it maximizes feature similarity between anchor image and positive samples, and also it minimizes feature similarity between anchor and negative samples. However, the contrastive pair sampling approach in conventional contrastive learning would lead to background bias. For example, here on the left-hand side, the conventional positive sample is generated by strong data augmentation to the anchor image of a dog in the middle. However, maximizing their feature similarity would also encourage learning background features due to their shared background information. Whereas in our sampling approach, in the right-hand side, we ensure no background information is shared between the positive sample pair and the anchor. On the other hand, in our sampling approach, negative samples share similar background information as the anchor. In this case, they both contain the grass as the background, which is a very typical background for the images of dog classes. Thus, when minimizing their feature similarity, the model is prevented from learning features from the background class. In contrast, in conventional contrastive learning, the negative samples can contain very different backgrounds as the anchor. In practice, positive samples can be generated by replacing the backgrounds in the image with a random background from a random class. These generated samples are stored in a negative sample dictionary according to their background labels. We define our negative sample dictionary as a dictionary with cues for each background class. These cues contain the latent representation for each negative sample. For each anchor, the negative samples are drawn from the dictionary such that all the negative samples have similar background as anchor. For example, when updating the dictionary, in the figure we have a generated sample containing the background of the fish. Hence, it's stored under the fish class in the dictionary, ignoring the foreground class. When drawing negative samples from the dictionary, here, for example, we have an anchor image of a dog. It draws samples from only the dog class in the dictionary, where all the images contain similar background information as the anchor. Finally, our model is trained end-to-end with the classification and contrastive learning loss. We can optionally include a classification loss for positive samples and refer to this model as CLAD+. As illustrated in this figure on the left-hand side, on each batch, we generate positive samples. Then, the generated positive samples are used to update the negative sample dictionary. The classification loss is calculated for the anchor, When calculating the contrastive loss, the negative samples are drawn accordingly from the negative sample dictionary based on the label of each anchor. The contrastive loss is finally calculated based on feature representations for the anchors, positive and negative samples. Our method achieves the state-of-the-art accuracy on the background challenge. Here in this figure, the y-axis represents the accuracy on a dataset with entirely random backgrounds. Hence, the main goal of the challenge is to get high accuracy on this dataset. The x-axis, on the other hand, represents a dataset with a background bias. Thus, the models closer to the identity line in this figure have higher background robustness. Our method achieves both best accuracy on the random background dataset and also the lowest background bias, outperforming all the existing benchmarks in this challenge and also other baseline models. From the saliency maps generated by SmoothGrad, we can see that both CLAD and CLAD Plus have a foreground focus, while the baseline models suffer from background bias. The saliency maps of CLAD and CLAD Plus are much cleaner with less background noise. For example, they are much less affected by the snow when recognizing the wolf image in the second row. In this slide, we show that our method CLAD can also be applied to the debiasing of other discriminate features. Here we take the image texture as an example, which might also be a spurious feature in image classification. In this case, contrastive pairs are generated by altering the shape and texture information instead, accordingly. Positive sample pairs share similar shape information, while negative sample pairs share similar texture information with the anchor. The models trained with CLAD have around 20% accuracy gain in both stylized images and also sketch images, which are both texture debiased datasets, compared to the baseline models. This shows that our method successfully reduces the backgrounds towards the texture. Thanks for listening. Our paper is available through this QR